Hello again, welcome to the Academy. This is a part of a video series on Cal 3 topics, and this episode we will be talking about Green's theorem. So previously I talked a little bit about line integrals, path integrals, and then about double integrals. In fact, there's a way to combine the two. So just a quick refresher of what we were talking about earlier. The double integral is the integral over some region R, dA, gives you the sum of the function, or you could say the volume under the curve of the function over this region R. When we're talking about path integrals, it was usually some function dot dr over some one-dimensional path C. But consider the case now where you have a closed curve. If C is a closed curve, usually draw this little circle. Then there's a region inside of it that we call R, and there's a relationship between the integral over the boundary path C and the double integral over R, and I'll show you what it is. But first, I want to show an alternate writing of this. Now, usually we talk about R, we said it was the position vector x comma y, the position of your point, whatever point it is on the path. And so dr, usually we substitute some variable t and get the derivative. Or an alternate way is without t, just dx comma dy. And if f is a vector valued function with L and M as functions of x and y, L and M are both functions in this case, then this, if you take the dot product of this and this, you just get that the integral is L dx plus M dy, and this is an alternate form of an integral, a line integral, and this is a form that is used in Green's theorem. And the theorem itself states this. If you have f is L and M, so if you have L and M continuous differentiable functions, then you have a closed region R bounded by a curve C going counterclockwise. Then the double integral over the region R of partial derivative of M with respect to x minus the partial derivative of L with respect to y dA equals L dx, standing by the integral of that over the curve C, which is the boundary of the region. So this allows you to take a single integral and transform it into the double integral of the region bounded by it if it's a closed curve. Or alternatively, if you want to calculate the double integral of something that is in this form you can simplify it to a single integral over just the boundary of the curve. And this is a generalization of the fundamental theorem of calculus, again, which, as we said before, talks about the integral of a derivative being just the function itself again, evaluated at the endpoints, which you can think of if there's an interval from a to b, the boundary is just the endpoints. But in this case, of course, it's more general. It talks about the integral of this form, which has these partial derivatives in it. This is a special, the reason for this minus and the switching of the L and the A, which we'll talk about later on. But basically, this is a differential form that has special properties. And so the integral of this can be simplified by dropping one of the integrals. There's one integral less. As you can see, just like here, the integral goes away. Here you have two integrals, become one integral of just L dx plus N dy of the boundary again. So it turns the whole region into just the boundary. Let's do some examples to show that it works. So let's consider L equals x squared, M equals xy. And let's have our region be this simple one, it's unit square, is a region R. And so we should get the same result on both sides if we evaluate. So let's try evaluating the double integral. So the partial derivative of M with respect to x, well, that's just y, minus the partial derivative of L with respect to y. Well, there's no y here, so it's just 0. And this should be equal to the integral over the region over the path C, which goes counterclockwise. Now this path has 4 parts. You can break it up into 4 straight lines of L dx, so x squared dx plus xy dy. Now this form helps you in several cases. You can divide this up into C1, C2, C3, and C4. And if we add them all together, of course, we'll get the full integral. And a lot of these will simplify. So in C1, x is not changing, it's staying the same. So if x is 1, so in C1 we have x equal to 1, and y goes from 0 to 1. And so dx, well, if x stays the same, dx is just 0. X is not changing. So dx is 0, that leaves just dy. If x equals 1 the whole time, this is just y dy. In C2 is the other way around. Y is constant at 1. X goes from 1 to 0. And so dy is 0 in this case, which just gives you x squared dx. C3, again, here x is 0, and dx is also 0, because it's moving only in the vertical direction. And since dx is 0, this becomes 0, and xy, well, x is 0, so this becomes 0. So this is just 0. So we don't even have to take C3 into consideration. C4, y is 0, so dy is 0, and x goes from 0 to 1. So dy is 0, this is 0, so it's just x squared dx again. So here, let's just calculate C1. For C1, we go from 0 to 1. Right, yes. So y goes from 0 to 1 of y dy, which is, calculate this would be y squared over 2, from 0 to 1, which is 1/2. Plus, well, x squared dx, C2, x goes from 1 to 0. 1 to 0. This is just going to be x cubed over 3. From 1 to 0, which will be negative 1/3. And this one was 0, is going to be from 0 to 1 of x squared dx, which is again x squared over 3, x cubed over 3, from 0 to 1, which is going to be positive 1/3. And these two will cancel each other out, so you're just left with 1/2. So that's calculating this part. We get 1/2. Now if we do the other way, using the double integral, or we just get integral of y dA, over this region is just a unit square, 0 to 1, 0 to 1, y, dx, dy, or dy dx, or it doesn't matter for this one. Becomes y squared over 2, 0 to 1, dx, which equals 0 to 1, 1/2, dx, which is 1/2. So we get 1/2 here and 1/2 here. And clearly now they're both equal to each other. So Green's theorem worked in this case. And in fact, as a side note over here, there was an easier way if we have this form. Intuitively, we could have actually gotten to 1/2 directly from this, just by inspection of this region, because if we integrate y dA, we're adding up all these y's. And so, and perhaps this should be important to note, that the center of mass, or the centroid of a region, is the average of all x values and the average of all y values. So really, if your centroid x bar, y bar, x bar will be the average of all x values in the region. So x dA divided by the area of the region. And y bar is the same thing. So the center of this one is right here in the middle at 1/2, 1/2. And so, since the area is 1, it's a unit square, 1 by 1 square. Therefore, we know that this is going to be 1/2, because this area here is 1, so y bar, which is the center of y, is the average of all y's. So it's the integral of y divided by 1, which is the area. But we know, of course, it's 1/2, because that's where the middle of the square is. So that was a simpler way of calculating this, but of course you can still do the calculations and get 1/2, which we did. Green's theorem is of calculating areas. You can calculate the area of a region by taking the integral of dA. And this is because integrals undo whatever this dA is. So the integral of dA is going to be a, and just like the integral of dx is just x, the integral of dA is a, but in this case a, we usually use two integral signs like I explained, because it's a double integral. An area is an area element, not a line element. We could write it like this if you wanted, but this is a more common form. And so the area of the region just by itself is just the integral of dA. Or 1 dA if you want, because you're just finding the volume of a thing that's just 1 in height. So the volume is just the same as the area times 1. So it's just really the integral of dA. This gives you the area again. But Green's theorem says that the integral, the double integral, can be simplified to a single integral over the boundary of R. R is a figure, a region, and C is the counterclockwise boundary of just L dx plus M dy. And so if we want to calculate the integral of just dA, we want to choose our L and M so that this is equal to 1. So there are several ways of doing this, but the easiest way really is if we make this 1 minus 0. So if we say what partial m with respect to x will give us 1, well, this is partial x with respect to x will give you 1. And if we want 0 here, to make this 0. And so this becomes just 1 dA, which is what we want. Simplifies to, and this is equal to the area, L dx, well L is 0, so that's just M dy, M is x, and just x dy. So if we have a complicated region, a simpler way to calculate it is just to take the integral of x dy. In fact, there are machines that were used in the past that you trace them around an object, and the whole time they would be calculating something like this, and then when you finished going around, they would tell you the area of the region. So really the area of the region, you can find it only by considering this boundary C. And we can, of course, do that. Just do an example. So a simple region, let's say a circle right here, diameter 1, and this is in polar coordinates. You can see this is equation R equals cosine theta, and this can be traced out in many different ways, but if you go counterclockwise, it will be from 0 to pi, should give you the entire circle. So of course we know the area of this is going to be pi over 4, because the radius is 1/2. But we can also calculate it like this. So let's try calculating it this way. Integral of x dy over this region And so x, if we put everything in terms of the angle of theta, then x is r cosine theta, and y is r sine theta. In this case, r equals cosine theta. So this is just cosine squared. And dy, well, if y is cosine theta, sine theta, and dy is going to be, if we use product rule, that's just going to be cosine squared theta minus sine squared, I believe. Yeah. Yes. So we calculate this, substitute these values, and this goes from 0 to pi. 0 to pi cosine squared theta, cosine squared theta minus sine squared theta d theta. So I can calculate this. Well, let's see. Now there are power reduction formulas that we could use. Or perhaps we should split it up into two integrals. Now we can use the power reduction formulas. We basically say that cosine squared is cosine of 2 theta plus 1 all over 2. Actually, perhaps it would be easier to substitute that directly in here. If we know that this is also cosine of 2 theta, this becomes the integral 0 to pi cosine of 2 theta plus 1 over 2 times cosine of 2 theta again, d theta. Alright, continue over here. Well, here's a 1/2 that we can bring out. That would just be cosine squared 2 theta plus cosine of 2 theta d theta. Here's 1/2. And go from 0 to pi. Cosine squared 2 theta plus the integral from 0 to pi cosine of 2 theta d theta. Now this one we can calculate just by substitution directly. It will give you 1/2 sine of 2 theta. But if we see this function we can see that this is half of the period because of the 2 in front of the angle, and the period is normally 2 pi, so half of it is just pi. So this is just the full period. If we integrate over the full period, well, we'll just cancel the whole thing out. It'll just be 0. And you can see that if we put in, we actually did the 1/2 sine 2 theta from 0 to pi. Well, sine of 2 pi is 0, sine of 0 is also 0. So this whole thing is 0. Now we have to do this, another power reduction formula. 0 to pi, cosine squared of an angle is the same thing as cosine of twice that angle, so twice of this is just going to be 4 theta plus 1 all over 2, so another 1/2. We out. Plus just the integral of d theta from 0 to pi. We split up the 4 theta and the 1. And we separate these two parts into separate integrals. Again, we see that this is going to be 2 periods instead of just 1, but again, it will just be 0. Integral from 0 to pi of theta is just pi, so it's 1/4 pi, which of course we already knew because it's a circle, another area of a circle. But there's another way of calculating it, and of course this becomes more useful when the shapes are not simple like circles, when they're more complicated, and it would be easier to calculate this integral than to actually do a double integral. So that's what Green's theorem. So I'm going to give you some interesting alternatives here. That's basically all for Green's theorem. Thanks for watching, and I'll see you in the next video.